Our next speaker is Uwe Karst from University of Münster in Germany. His talk is Identification and Quantification of Reactive Metabolites and their Adducts using Electrochemistry coupled with LCMS. Co-authors are Wibke Lohmann, Anne Baumann, Sandra Jan, and Bjorn Meerman.
Well, thank you very much, Anne, for the kind introduction. Ladies and gentlemen, I would like to separate my talk into two different parts. The first one will deal with the generation of metabolites by using electrochemistry coupled to mass spectrometry, and the second part will be directed more towards the quantification of these compounds. Well, if we look at the metabolism of drugs, most of you will know that we have two phases which we normally consider, the phase 1 and the phase 2. Phase 1 typically consists of functionalization reactions, which are catalyzed by the cytochrome P450 enzymes. Phase 2 is then a further conjugation reaction, which makes the compounds more polar. This is catalyzed by transferases, and then we get the phase 2 metabolites, which are easily excreted from the body. If we look at the metabolism studies, then normally we have a quite easy game when looking at stable metabolites, because the drug compounds are metabolized to stable compounds, which can then be isolated and be identified by the whole array of structural analytical methods, including UV-Vis, NMR, and so forth. For reactive metabolites, the situation looks much worse, because the drug is converted into reactive metabolites, and these reactive metabolites may bind to proteins, and that means in all studies where biological systems are involved, we have a serious chance of the formation of protein adducts, and at this stage it's quite difficult to isolate the compounds and to structurally elucidate them. Typically, these compounds are then identified indirectly, and that means the drug is just made into a reactive metabolite, and this is added, to this added a trapping reagent, and this trapping reagent forms a trapped metabolite, which is then isolated and structurally characterized by NMR, tandem mass spec, UV, and infrared spectroscopy. A typical trapping reagent is glutathione, which is also inherently present in the body. This is a very nice reagent for the quantification, identification of the trapped metabolites after reaction with this trapping agent. So we have no direct detection of the reactive metabolites, and only the trapped metabolites can be characterized. That means that if we would look at the direct detection of reactive metabolites, we would of course do the detection directly after generation, which means that we need an online method for their characterization. And of course we would like to exclude the binding to macromolecules, which means that a purely instrumental method is significantly preferred. Therefore, the approach which we are using is that we use a reactor system in which the reactive metabolites are formed. They are then online separated by HPLC and detected by mass spectrometry. If you look at the oxidation reactions which are taking place in the body, then they are taking place in the liver by the cytochrome P450 enzymes. And the typical reactions which you observe are hydroxylations, dealkylations at the heteroatoms, dehydrogenations, oxidations at heteroatoms, epoxidations, and oxidative deaminations. A couple of further reactions are observed as well. And what we'd like to do is simulate these reactions by an in vitro method. Currently, people are using in vivo methods, for example, laboratory animals and their analysis of urine and plasma, but also in vitro methods based on liver cell microsomes and also hepatocytes. We would like to replace now the liver cell microsomes by an electrochemical cell to simulate the oxidative metabolism of the compounds we are looking at. And in the electrochemical cell, due to our experience, you can simulate the majority of these reactions listed over here. What you cannot do is, for example, the epoxidation. What works very nicely are hydroxylation reactions and dealkylations, especially at the nitrogen, and also dehydrogenation reactions. I will show you some examples for that in the near future. The electrochemical cells which we are using are on the one hand the so-called coulometric cells, which are shown here on this graph, which are available from ESA Biosciences, but also the thin layer cells, which are available from Antec Leiden in the Netherlands. So both of the cells are doing quite a good job in our lab, and we are using both of them. The coupling of electrochemistry to liquid chromatography and mass spectrometry is typically carried out using such an arrangement. So we are using a syringe pump transporting the drug in solution through the electrochemical cell where the potential is controlled by a potentiostat. We are loading an injection coil over here and then just inject the whole mixture from the electrochemical cell into the LCMS system. The reason to decouple this is quite obvious. We then have the possibility to undergo both steps of this approach under the optimum conditions. So we can use the optimum conditions for electrochemistry on the left side, and we can then use the optimum separation conditions on the right side in the LC system. We obtain information on mass to charge ratios, polarity, and also of the isomers of electrochemical metabolites. Especially polarity information from the LC system is very helpful because then we can see if there's not only one metabolite form, but if we have an array of metabolites, which is important in some cases. I would like to go now through a couple of examples for different approaches related to electrochemistry. And this is an approach where we look at a bioactivation reaction instead of a detoxification, which means we have the formation of a reactive metabolite from a comparably stable mother compound. We're looking here at the anti-tumor agent amsecrine, and if you look at the upper part of this molecule, you see here a diamino system and an aromatic ring. And this is a system which can easily be oxidized under formation of a quinone diamine. This occurs under bioactivation of the cytochrome P450 system, and this compound here is a reactive metabolite which can add thiols, for example, and other reactive compounds. If we look at the different approaches in LCMS, this is just an injection of the amsecrine standard, and you see that there's just the pure compound visible. In electrochemistry, we have the pure compound reduced, but another compound appearing. In the microsomes without glutathione, we have mainly the parent compound, just a tiny peak additionally. With the microsomes under addition of glutathione, we again see mainly the parent compound plus another peak. What is hidden behind that? Of course, the mother compound as indicated below. Then for the electrochemistry, we see the quinone diamine directly, so this compound over here, which is not visible in the other approaches. And that means that we can directly detect the reactive metabolites without any trapping. In the second part here, we see just the glutathione adduct under the use of glutathione and the microsomes. And that means that in this case, we have to do the indirect steps, so we cannot directly detect the quinone diamine, but we can only detect it as an adduct with glutathione after trapping. Further information on this technique is available in this publication cited over here. We have then looked at protein adducts of the reactive metabolites, and in this case I would like to give you an example for amodiaquine, which may covalently modify proteins. The reaction which we're looking at is the following one. We have the amodiaquine over here. It is activated again to reactive metabolite, in this case a quinoneimine. And this quinoneimine can now react with free thiol groups in proteins under formation of the respective protein adducts. Now I'd like to show you this for an example, a simple example in this case first with beta-lactoglobulin A. We are doing most of our protein adduct studies first with beta-lactoglobulin A because it has just one free thiol group and it's very well accessible to mass spectrometry. So it's much better from the mass spec point of view compared with human serum albumin, but of course it's not relevant for the biological systems. So it's a very good model system for initial tests, and we always do it. So if we look at the unmodified beta-lactoglobulin A here, then we deconvolute the mass spectrum to obtain an M/Z ratio for the whole protein of 18.36 kilodaltons. If we then do an adduct formation with amodiaquine quinoneimine, then we get another mass spectrum. It's already significantly different from what you see here in the spectrum itself. If you deconvolute it, you get an addition of a mass, and this is exactly fitting to the mass of one amodiaquine quinoneimine. The interesting thing over here is that you can really quantitatively do the adduct formation. So it's really nice to do an adduct formation even at the protein level of these reactive metabolites. Of course, it's interesting to see where the location of the modification now indeed is. It is, of course, to be expected that the free thiol group of the beta-lactoglobulin A will be the binding site. And so we just did one simple experiment in the very beginning. Beta-lactoglobulin A contains two disulfide bridges in addition to the free thiol group. And that means that if we reduce the disulfide groups, then we have a total of 5 free thiol groups, and in that case, indeed, we get up to 5 modifications, so typically between 3 and 5, and with the highest concentration at 5 modifications. Afterwards, we did a triptych digest of the modified protein to identify the binding site, and then you can really find out the location. In this case, it could be easily assigned to the binding site which was originally expected. If we then look at the much more relevant and more abundant plasma protein, the HSA, the human serum albumin, which is the most abundant protein in the human plasma, then the situation looks much more difficult on the MS level. I've just cut out here part of the mass spectrum, and you can see already that you have quite a broad distribution of charges. What we see here in the human serum albumin is a structural inhomogeneity, which is based on the fact that the HMA, the human serum albumin, is called also mercapt albumin because it's got its free mercaptor group. If you have the binding of another cysteine, it's the so-called non-mercapt albumin, HNA. And normally you should expect that with the compounds which bind only to thiols, you should see an adduct formation only with the HMA. On the other hand, if you look at the adduct formation with clozapine, which can be converted electrochemically in this nitrinium ion, then you see that the HMI, so the group with the free thiol, is almost completely converted into a respective protein adduct, while the HMI is also reduced. There's also a certain part converted into a modified protein. And that means that this reactive metabolite over here, in contrast to the quinondiamines, is also possible to a lesser extent to bind to free amino groups and not only to thiol groups. So this is another example what protein modifications are possible using this approach. I would now shift to the second part of my talk, to the qualitative and quantitative information. And I'm looking here at the model compound amiodarone, which is an antiarrhythmic agent. This compound contains 2 iodine atoms and also some sites which are typically cleaved by N-dealkylation. So these are the typical sites for metabolism reactions, and also the deiodination may be observed. The question is, of course, which metabolites are formed, and also, on the other hand, what is the concentration of the formed metabolites. And I would like to show you here an approach which is unusual, at least for the combination with electrochemistry MS. We are using, again, the synthesis of the reactive metabolite in an electrochemical cell coming from a solution of the reagent. The electrochemical cell, again, controlled by potentiostat. We are injecting everything to an injection loop over here, switching that over the column, and then we can go to either the electrospray MS or the inductively coupled plasma mass spectrometry to obtain, on the one hand, qualitative information, so the identification of the compounds by electrospray mass spec, and the quantification of the compounds by the inorganic, so the ICP mass spec. In that case, ICP is very nice because ICP is completely substance independent in the quantification. So due to the fact that you are atomizing the compounds in a very hot plasma, only the atom concentration is significant, which means there is no effect by the history of the compound. For example, for a compound which has been in an organic state, you get the same signal as for an inorganic compound. It's completely different to what Philip already mentioned for the field of electrospray MS. Okay, this is something which you obtain then in electrospray mass spec at a very high potential. You see that quite a number of metabolites are formed. This is the parent compound itself, and you see it deethylated, you see deiodinated, you see bis deethylated, the combination of both, and so on. So all of these metabolites are observed. If we now look at ICP-MS, we mainly see, and you should consider that the scales of the y-axis here are different. You see at a potential of 600 millivolts, so low potentials, mainly the parent compound and just the deethylation. While when you look at higher potentials, you see an almost complete mineralization of the compound, which is detected by the fact that you almost exclusively see the inorganic iodine species over here, which are iodide, triiodide, and also iodate. If we look at this in another display, then you can see here the different compounds. So the parent compound, deethylated, deiodinated, bis deethylated, and deiodinated, and the inorganic iodine compounds at different potentials. You can see that at the lowest potential, the amiodarone is completely unchanged. But if you go to higher concentrations, then you come to the formation of deethylation products first, and then later mainly to the inorganic species, which is the same thing which I showed you before, but just another form of display because it's a bit more obvious over here. I would like to come now to the last part of my talk. This is the oxidation of milazoprol, which is used for the treatment of the human African trypanosomiasis, which is the sleeping sickness. And this is known to form an active metabolite, which is the melazine oxide. And this is known to inhibit the tryptophan reductase. This is the metabolite over here. And this compound has very severe side effects, especially in encephalopathy, in a concentration range of 2 to 5% of the patients. So it has very severe side effects and is for that reason not very popular in its use, but it cannot be avoided. If you look at the analysis of the milazoprol after electrochemical treatment at 1250 millivolts in this system, then you can see different peaks over here. The parent compound is shown here in electrospray. Then the melazine oxide is shown over here. And you can also see an oxidation at the arsenic. So that's, so to say, the direct oxidation of the parent compound. And this is also quite a nice peak over here. If you then look at the electrochemistry coupled to ICP-MS, then you see the same peaks again. Here again the milazoprol, then here you have the milazoprol in the oxidized form, the melazine oxide, and this is also inorganic arsenic species. So you can see that also a certain amount of mineralization takes place under these conditions over here. This has been followed at the M/Z ratio of 75 for arsenic. So the inorganic arsenic species are shown over here. This is again shown in a mass voltammogram. So what you see here is the chromatographic time axis, the different potential, and you can see that the milazoprol is first converted into the oxidized product, so with the arsenic oxidation, and then later also to the inorganic arsenic species, which means mineralization. I hope that I was able to show you that the online electrochemistry LCMS method offers the direct detection and also the structural elucidation of reactive metabolites. That it is also possible to synthesize reactive metabolites and also their reaction products in high yields and good purity for further studies. That the generation of protein adducts in high yields is also possible to study the tendency of these compounds for covalent protein modification. And I showed you also that the protein quantification of heteroatom containing metabolites is possible using the combination with ICP-MS. Thank you very much for your attention.
We do have time for questions, so yep, go ahead.
So one question over here. One question is, you didn't show data that correlates, say, microsomal incubation versus your electrochemical detection. I wonder if you could give us a number, like a percentage of the time that the actual metabolites from reagents, living reagents, are produced by the electrochemical detector.
Yeah.
Because there's a major issue here of metabolism being a regio-specific event, dependent upon the binding of the compound to the enzyme first, and then the reactivity. So you've got the reactivity component, but you don't have the regio-specific.
Yeah, true. But actually, of course, you cannot compare this in all cases. That's what I said in the very beginning. You have surprisingly high correlation between the two approaches. And what should also be pointed out, in some cases, people are assuming that the liver cell microsomes are somehow the truth. This is not fully correct, because in many cases you will not see the reactive metabolites, because in the liver cell microsomes the reactive metabolites will bind to the proteins in there, so you'll not see them unless you add trapping agents. So that's one of the reasons also which are advantages for electrochemistry compared with liver cell microsomes, and which also of course leads to deviations between these two. So in many cases you're fully right, the stereoselectivity cannot be simulated, but also some of the things which are accepted for the liver cell microsomes are traditionally accepted, but they are not really scientifically more sound than the electrochemistry, because the reactive metabolites cannot be simulated very well in these approaches. So I think both of these approaches have their justification, and I think the electrochemistry will not be able to replace the traditional approaches, but it's a very nicely complementary information, especially for rapid simulation of these reactions and also for the simulation of reactive metabolites.
Another question?
There are very few pharmaceuticals that contain iodine or arsine. However, there are now more and more compounds that contain fluorine. So my question, do you also have an example with fluorine where ICP-MS gives quantitative results?
Well, the problem simply is that ICP-MS, if you look at the plasma, in the plasma you get a protonation, you get an ionization of the compounds by the loss of one electron, which means you get the cation. And that means that all the elements which are more electronegative will hardly be ionized. And especially fluorine is very hard to ionize. There are just very few papers, for example, from the group of Gary Heaftje quite a while ago, where they looked at the ionization of elements like fluorine. So for fluorine, it's very unfortunate that this is not possible by ICP, because the limits of detection are extremely poor. You can see it under certain conditions, but you can certainly not see it in concentrations which are relevant for these studies. This is simply due to the chemistry in the plasma, because you just kind of take out one electron thermally. I mean, if you heat a compound, you just emit electrons, so you come to the cation, and the cation itself will not be formed easily by the electronegative elements.
Thank you.